Hey everybody, welcome to a video on section 9.4. In this video we'll talk about a model of competing species. So this model is one of two final applications in the course. We'll talk about competing species in this section and then predator-prey interactions in the next section. So the point of this section is to build a system of differential equations to model the interactions of two competing species. Once we have that model, we can analyze it using the tools from the previous sections from chapter 9. So let me just start by giving you the general setup, what are competing species, and let me build the differential equations for you. So let's let x represent the population of species 1 over time, and let y represent the population of the other species. We assume that these species are competing for the same food source, but they don't prey on each other. So it's merely competition for food. They're not eating each other or anything. So just for example, X might represent the population of bears, and Y might represent the population of wolves in Yellowstone National Park. Or a lot of times you'll see these models used to talk about competing bird species. So X might represent the population of a small beaked finch, and Y might represent the population of a large beaked finch on a Galapagos island. This is sort of the framework for these models. Before building a model, we should always start with the disclaimer that we always start with when we do math modeling. Models are approximations of reality. You have to make assumptions that don't necessarily match how reality looks, right? They are simplifications. Therefore, they are only useful insofar as you don't approximate too much. So of course, if you want to build a model involving two competing species, you're going to lose some information. However, these models are useful. They're a nice heuristic. They're a nice way to approach the problem of modeling the interactions of two competing species. So these models still have value, even though they are, of course, simplifications of what actually occurs. And moreover, if you want to do more complicated modeling, you would have to start here. You have to start with the more simple models in the hopes that maybe you can build more complicated ones to do less approximating in the future. So the first step in building a model, as always, is to state your assumptions. The model you build flows from those assumptions. So there are two species who compete in a closed environment for the same food source but don't prey on each other. X and Y have already been defined. So here's our first main assumption. In the absence of the other species, a given species will grow logistically. So if Y equals 0, so there is nothing from population Y in the system, then X of t, that population will grow logistically. And here we see an echo from chapter 2, right? Recall back in chapter 2, we spent quite a bit of time actually, section 2.5, with models that had logistic growth in them. So here's a logistic equation. We didn't write the logistic equations quite like this back in chapter 2. We had like an X over K, where K was the carrying capacity, and we had like this epsilon kind of factored out to get a growth rate on the outside. However, if you flip back to chapter 2, this is what we were looking at back then. Okay, so all that to say, if there's no y's, then the population of X will basically approach its carrying capacity as governed by this logistic differential equation, and same for Y. If there are no X's around, population X has died out, then Y will grow logistically according to its own logistic differential equation. So notice the constants here, these parameters are different. So the carrying capacity for X might be different than the carrying capacity for Y. The growth rate for X might be different from the growth rate of Y. So each species has its own logistic equation governing its growth in the absence of the other. Well, what if both species are present? This, of course, is what we usually care about, right? How will they affect each other? We assume that each species will tend to diminish the available food supply for the other because they're competing over the same food source. So the way that you can model this kind of interaction is actually very SIR-like. This is very nice, right? These differential equations we're going to build will have terms in them just like the SIR models had in them. So if you think about X, for example, so X prime, here is the part governing the growth of X. This is the logistic DE governing its growth. But then notice you take out a term like this, alpha 1 XY. So what's happening there, that term is basically modeling the interactions between the species. So the more the species interact and the more competition there is, the higher, like the more you're taking out of the population of X. So this alpha 1 parameter here, it's sort of like an effective contact rate from the SIR models. Not literally, but alpha 1 is sort of modeling how much interaction there is between the two species and sort of how good X is at outcompeting Y. So if alpha is really small, that would mean species X is good at competing with species Y, right? Because this minus term would be smaller. If alpha is large, that means that Y is better at competing. Okay, so back in the SIR models, this sort of term, you would see like a flow from X to some other population. That's not happening here, of course, right? These X's, when they flow out of the system, they're just dying out. These X's don't become Y's or something, right? So again, this isn't literally like an SIR term, but it's the same idea. The interaction between the two species causes some individuals to leave the X population. And similarly for Y. So alpha 2 here is sort of a measure of how good Y is at outcompeting X. How much might Y lose from their competition with X? And again, these parameters might be different. So alpha 1 and alpha 2 have to be given different names. So anyway, you have logistic growth minus not growth. I'm blanking on the word. The opposite of growth here, right? Where that dying out or the declining comes from interactions between the two species. Once you have your differential equations written down, you can then factor out variables like there's an X there and an X there, so you may as well pull it out. Y there, so pull it out. So here are our two DEs modeling this growth of two competing species. So epsilon 1 kind of contains a growth rate, sigma 1 contains sort of a carrying capacity, alpha 1 contains sort of a competition number, how much are the two species interfering with each other and how bad is that for species X. And then Y has its own 3 parameters. So this is nice. It's basically saying, well, take the logistic models from chapter 2, which we spent some time thinking about, and modify them with an SIR, sort of contacty interaction kind of term inside the differential equations. Let's look at an example. So let's let X represent the population of bears, Y represent the population of wolves. In Yellowstone National Park, these two species are in competition in that national park, right? There are both bears and wolves there. They, generally speaking, compete for the same food sources like deer and rabbits and things like this. I don't know. The model determining the growth of these species over time is given below. So this is just a made-up example, okay? In practice, you have to try to estimate all 6 parameters empirically. So epsilon 1 is a 0.6 in this example. I forget what letter was here, but that's estimated to be a 1, negative 1. I forget what this was called. It's a negative 1, right? So here's an epsilon 2. Let me see what they're actually called. Oh, sigma and alpha, right? So sigma 1 is assumed to be, so the minus is baked in, right? So the sigma 1 is assumed to be 1, and then the alpha 1 is assumed to be 1 also. Anyway, so in practice, you try to estimate those by looking at some data. We're skipping that step for now. Okay, so also worth noting, things are measured in thousands so that basically the numbers stay manageable. So here's a question, right? If today, right, we measure the populations of both those species in Yellowstone and there are 60 bears and 140 wolves, what do you think will happen over time? We have seen in section 9.3 that the way to answer that question is to classify the equilibria. You find the equilibria, classify them, that gives you an idea of how the system is behaving overall. So again, to answer this question, one thing you could do is solve this system. Like literally solve it, right? Get a formula for X and a formula for Y, and then you could figure out what X and Y are doing at any particular time you want. However, this nonlinear system here is pretty hard to solve. If you wanted to quote solve it by getting graphs, you could use Euler's method on it like we did with the SIR models. But that's kind of perhaps unnecessary in this context. And if you want a formula for X of t or a formula for Y of t, that can be very hard to get. So just like back in chapter 2, we're not going to try to solve these sort of for real. We're going to get an idea of the long-term behavior of the solutions using equilibrium analysis. So here's chapter 2 all back up in your face, right? Except now we have systems of DEs, not just a single DE. But it's very nice, right? The parallels back all the way back to chapter 2, to the beginning of the course. So let's do the equilibrium analysis. So if you want to find equilibria, set the derivatives equal to 0, ask Wolfram to solve this system for you, and Wolfram spits out these 4 points. So mutual extinction is an equilibrium. Right, that makes sense. So recall, an equilibrium is a solution to the system, right? So if we have no wolves, no bears, then over time we will continue to have no wolves, no bears, right? Where are they going to come from? We're assuming a closed system and blah, 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 right? So X is bears, Y is wolves. Okay, let me not get that mixed up. So anyway, this is like saying no bears, no wolves. This is saying 0.6,000 bears. So that is 600 bears, no wolves. This is saying no bears, 560 wolves. This is saying 100 bears and 500 wolves. All 4 of those, if you're at one of those points, you'll just stay there over time. Here are the 4 equilibria. So mutual extinction, the wolves being gone, the bears being gone, and then a mutual coexistence equilibrium. Let's classify them. Let's start with the coexistence one. Let's see if it's, for example, stable or not. Okay, so you do just what we did in section 9.3. So I'm not going to go through the details here because we're just doing what we did in the last video. So you build a Jacobian like this. So this is the partial derivative of this dude right here with respect to x. This guy right here is the partial derivative of this highlighted stuff here with respect to y, and so on. Once you have the Jacobian built, you can then plug in any equilibrium you want into that. So if I plug in 0.1 and 0.5, I get this matrix here. So just like back in section 9.3, this nonlinear system here, near this equilibrium, will behave like the linear system corresponding to this matrix. So as long as we know what this matrix means, then we understand what the system is doing near this equilibrium. This matrix has 2 distinct negative real eigenvalues, which means that in this bear-wolf system, right, this mutual coexistence equilibrium is asymptotically stable, and it looks like a node. And if you want to know exactly what that node looks like, you can find the eigenvectors. Since we're here, let me just go ahead and hop over to the slope field for this. Okay, so the blue arrows are the slope field, and then the 4 red circles are the 4 equilibria. So right here is the coexistence equilibrium, and you can see that node behavior, right? So here's a dominant eigenvector right here. Things are flowing to that vector and then flowing into that point. And you have sort of like a non-dominant one, kind of like this, it looks like, right? Flowing away from. So you can see that node structure right here. I would zoom in on it and show it to you more, but this program has recently been persnickety on my zooming. Sometimes it won't let me zoom back out. Anyway, so you can see the stability in this picture, right? If you're at this red circle and I knock you off of it a little bit, you flow right back, don't you? No matter which way I knock you off, you flow right back. So there's an asymptotically stable node there. Okay, so you can see what happens from the picture, but your first exercise should be to repeat this analysis for the other 3 equilibria, and then use all of that information to make a prediction. Our question was, if you have 60 bears and 140 wolves initially, what happens over time? So do the classification and then try to answer this question. Okay, so assuming you are back, you should have gotten that these 2 guys are unstable saddles and the mutual extinction equilibrium is an unstable node. So if what you want for Yellowstone is for both bears and wolves to coexist there, then this is all good news, isn't it? Right? Because you want instability, whatever, for these equilibria where there's zeros, right? That's a bad outcome. This one especially is bad, isn't it? Right? So you especially want that guy to be unstable. These 2 guys also you'd like to be unstable if you want both wolves and bears to coexist. Because what does that mean? This guy being unstable, for example, like think about this guy. Since that guy's unstable, if I knock you off of it a little bit, then you're not going to flow back. You're going to flow away. And where are you going to flow to? You're going to flow to a stable equilibrium. And in this case, the stable equilibrium is mutual coexistence. So what does it mean to knock you off this point a little bit? Suppose I replace that 0 with a 0.1, like I reintroduce some bears into the system. Things aren't going to die out. They're going to flow to this guy, we think. Right? It all depends on the model. Assuming that these parameters were estimated properly, right, were estimated well, then you can predict mutual coexistence. Okay, so anyway, so in sum, there are 4 equilibria, one of which is an attractor, the others are repellers. We predict, therefore, that the wolf population grows to 0.5,000, the bear population grows to 0.1,000 over time. And if you want to see this play out, here's that slope field again. I'm going to plot the point corresponding to our initial condition. So this green point down here, the initial population of bears is 60, the initial population of wolves is 140. So you can see what happens, right? I flow this way. So the wolf and bear populations both go up at the same time. So bears, recall, are the horizontal axis, wolves are the vertical axis. Both of them increase. And then all of a sudden, right around here, the bear population actually just starts to die out a little bit while the wolf population keeps going up. So as you follow this trajectory, the y variable is always going up. The bears, though, like they kind of course correct or something. They produce too many bears all of a sudden, right? And so the system can't handle that many bears, so some of the bears die out, and you arrive at that point there. So this is all very nice, right? Like the tools of section 9.3 let you make these predictions based on the slope field, right? You can sort of see what the slope field would be. Okay, so let me just show you one more example, and then we'll be done with this section. Yeah, so both populations fall to that equilibrium if you start with more than, right? Sorry, I should have said there's another question here. What if you start with more than, right? Then you can start to see the fall. Basically, these two initial populations are too big for the amount of resources available. So you'd have to, this guy would fall to 100, right? This is like a 0.16 would fall to a 0.1, and this is like a 0.72, which would have to fall to a 0.5. So anyway, you can make whatever prediction you want given some initial setup. Oh yeah, sorry. Before moving on to the next example, here's a phase portrait, not the slope field, right? Here's a phase portrait of that system. So the numbers are a little different from the ones in the book. I wanted things to be a little make a little more sense given a bears-wolves context. But this is the general picture you want, right? You got some equilibrium in the middle that's coexistence. You have a node that goes like this, where basically the dominant eigenvector line kind of connects the equilibrium on the y-axis to the equilibrium on the x-axis on some level, right? And then the trajectories all flow to that and go into that mutual coexistence point. Okay, so again, this picture here, the actual numbers on the axis are a little different from the example I just did. But again, in this example, with wolves and bears, it doesn't make sense for this 1 and 0.75 to be so close to each other maybe, right? And this coexistence equilibrium doesn't make so much sense for there to be just as many bears as wolves, right? This is like 0.5, 0.5. In our example, it was 0.1.5, right? It makes sense to have fewer bears than wolves. Anyway, so just take away from this picture the general behavior here. Okay, so I'm finally done jumping the gun. Let's move on to our second example, just to show what else can happen in these systems. So in the previous example, we had mutual coexistence being stable, asymptotically stable. Is that always the case? Let's just think about that in this example. So here, the context doesn't really matter, but you have small beak finches and large beak finches on some Galapagos island. Here's the system now. Let's do the same thing, equilibrium analysis, to answer a predictive question, right? Suppose there are 750 small beak finches up front and 1,100 large beak finches up front. So if that's what we measure today, what do we predict will happen? So a big note here, you'll be asked this on your exam over this, or your mini exam, whatever I'm calling it, over this material, and you have to do the equilibrium analysis to answer this question. Okay, so I'm just saying that up front. So any of these questions goes the same way. You find the equilibria, you classify them. So this system has 4 equilibria. Again, you just ask Wolfram for this information and it spits it out. So there's, again, mutual extinction. You got a couple of equilibria where one of the populations dies out. I'm sorry, there's a typo here, right? Which of these is wrong? Let's go find out. I just typed it wrong from Wolfram. Sorry. This is what happens when people are forced to put courses online quickly, right? The professional quality is perhaps not there. So let's just ask Wolfram for this. 0.5. Ask it to solve that. Has to think about it. Oops, because I put that parentheses the wrong way. Okay, so sometimes Wolfram does this little and symbol. I'm not sure why. So x being 0 and y being 2. Half, half. X being 1 and y, yes. Okay, so we see what I did here, right? This 2, 0 should actually be a 0, 2, corresponding to this guy here. So sorry about that typo. Should be a 0, 2. Anyway, okay, the Jacobian is this. So you can, again, plug in whatever equilibrium you want, assuming your equilibria are correct, right? Plug in whatever equilibrium you want into that Jacobian, and now near half-half, I get this linear system. That matrix has eigenvalues of 0.16 and negative 0.78. So these are distinct real eigenvalues of opposite sign, one positive, one negative, giving you now an unstable saddle. So this is not asymptotically stable. So in this case, in a system like this, again, it all depends on whether you have like estimated these parameters well, but assuming these parameters are correct, what you're saying is that it's very hard for these two species to coexist on this island because the coexistence equilibrium is unstable. If I knock you off of this a little bit, we're thinking you won't flow back. You got to flow somewhere though. So you're going to flow to one of these other equilibria, all of which are bad if you like both of these populations. So what I want you to do now is pause the video and classify the other three equilibria where, again, this is 0, 2, not 2, 0. Okay, so assuming you're back, all three of them are, or sorry, two of them are asymptotically stable. Mutual death is unstable, which is nice, right? But these two guys are the stable ones. So in a system like this, we would expect to see flow towards that or that. And notice I didn't make the typo here. So let's go look at this real quick. Okay, so here's the slope field for this example. Oops, sorry. So notice that in this system, the origin is unstable. So if neither species exists and then I introduce one or two of them, right, you'll flow away from the origin. They won't just die back out. This guy here, though, notice, is also unstable. So if you're at the coexistence equilibrium and I knock you off a little bit, I suppose I knock you this way, right? What happens? You flow here, which is the dominant eigenvector line of a saddle, and then you flow this way. So you flow up to 0, 2. Or what if I knocked you down like this, right? Well, now you're flowing to this equilibrium. Notice, just like with any saddle, there is a possibility of returning to the saddle if I knock you off so you're precisely on the less dominant eigenvector line, which appears to be like that. If I knock you that way, you actually can flow back to the coexistence equilibrium, but that's a pretty rare occurrence, right? So again, what we're saying is that it's hard for these two species to coexist in this system. So the original prediction I asked you to think about, let me just plot that green point. So what happens to this green point, knowing that this is a unstable saddle with flow that way and flow that way, right? We know that that's the dominant eigenvector line. We know this guy will flow this way, this way, this way, and then zoop, get sucked into that point up there. So both populations will die down some, and then the X population, which is the small beaked, will keep dying out. However, once you reach around here, what must be happening is there's so few small beaked left to compete with the big beak ones. So suddenly, the large beaked ones can outcompete the small beaked ones, and the large beaked population goes up, whereas the small beak keeps dying out, right? Leftward movement means dying out for the species down here. So again, right here, there's just far too many birds for the resources available. So you'd predict some dying out of both of them, which is what happens. So you kind of tick downward and to the left if you follow those arrows. But again, whatever the species Y is, this large-beaked finches, they're able to outcompete and then eventually go to this equilibrium here where species X is gone. So that's what you would predict for these two populations, given that equilibrium analysis. So here I say the populations won't flow towards coexistence. Again, there's a little asterisk on the won't, because with a saddle, an unstable saddle, if you're precisely on that that non-dominant eigenvector, you can actually flow back to the point. But again, that's very rare. So if you want to see exactly what those eigenvectors are, here they are. The first one's dominant, so trajectories flow towards that. The other one's not dominant. So if you go back to this picture, see where it is. Okay, so think about this eigenvector here, 1, negative 1.3. So if I'm at this point, I take one step over and like negative 1.3 down, and I'm doing like this, if you extend that vector out. So again, I'm at this point, like over 1, down negative 1.3, gives me like an arrow like this. And if you extend that arrow in both directions, you get this dominant eigenvector line where things flow to that. This guy here, 1.568, so you go over 1 and then up a little bit, you get an eigenvector line like this. That's why you're seeing some possibility of returning back to this red point along a line like this. It's that less dominant eigenvector. If you want a phase portrait of this, here's what you get. So notice there's sort of like a dividing line between where things flow down to this equilibrium here at 1 versus this equilibrium up here at 2. There's a fancy name for this sort of dividing line. It's called a separatrix. And that line right there is defined by the less dominant eigenvector. So this is the less dominant eigenvector line along which it's possible to flow back to this point. So if you're sort of above this black line, you flow up to there where the X population dies out. If you're below this black line, you flow down to here where the Y population dies out. So in summation here, with competing species models, there are basically two types of behavior you expect to see. Either way, you expect to see basically 4 equilibria. You can have both species dying out, one or the other species dying out, and then coexistence. The question is really just that coexistence equilibrium, is it asymptotically stable or not? Do you get a stable node or an unstable node? So it just depends on those 6 parameters that you plug into the model. But generally speaking, these are the 2 types of pictures you will see. You'll see a phase portrait like this, which is unstable for coexistence, or a phase portrait like that, which is stable for the equilibrium. Okay, so in the next video, we'll talk about not competing species, but predator-prey, so where species X or Y preys on the other.